Bismillahirrahmanirrahim. In this lecture, we will study the rules of calculations of probability and use them to make some elementary calculations. So the title of this lecture is Probability Laws. Basically, there are two laws that we are going to discuss. One is the addition law and the other is the multiplication law. You probably are already familiar with these laws, but we will just go through these one more time quickly. Now, we have discussed in earlier lectures the concept of a random draw. A random draw is you have a population, you pick one person from this population, all people have to have equal chances. Now, in this setting, you can use from the start you're picking a person, but the person has many characteristics. So he can have a height, he can have a weight, he can have an age. So all of these are random variables. And once you draw a person, then you can ask, what is the age of this person? That's one random variable. Height is another random variable. Sex is another random variable. So many different types of random variables can come from this random draw. Now we go to just one small extension of this. The random variable is different from a random draw in that it also has a set of outcomes. The set of outcomes is the population, but instead of having equal probabilities, you can have a different probability for each element. That's all. There is no further big difference. So for example, a random variable has just two outcomes, 0 and 1. Probability of 0 is 1/4, probability of 1 is 3/4. So now this is not a random draw because the two elements are not equal. One has more probability, the other has less probability, so it's a random variable, it's not a random draw. But this random variable can be converted to a random draw. If we put in 4 elements, 1 is 0 and 3 are 1, then they all have equal probability, and so now this will be exactly like the random variable. But there are some situations where you can't do that. So example, if the probability of 1 is 1 over square root of 2, this is an irrational number. So that means no matter how many tickets, there is no fraction which will be equal to 1 over root 2. But in this case, we can approximate. So 1 over square root of 2 is actually 0.707 and more fractions, but 707 is a close approximation. So we can say that, okay, if I have 1,000 tickets in my box and I put 1 on 707 of them and 0 on 293 of them, then this is approximately equal to this random variable. So the concept of a random variable is slightly more general than that of a random draw. And now the third thing which I am going to say is that, so we start with random draws, we extend to random variables. The third thing is that this is all you need. In this I am taking a different approach to probability from the one that is universally in use currently. So in current probability texts, you have many more types of random variables. You have discrete, you have continuous random variables, you have infinite. So as far as we are concerned, the only thing we need is just this concept, and this is all. Everything else can be approximated by a random variable, and so this is our fundamental and main and essential and basic and core concept of probability. Nothing else is needed. And this is random variables, very simple to understand intuitively as opposed to the more complicated material. Okay, so now we come to the laws of probability. The laws of probability are so simple that they don't even need to be really mentioned because it's almost obvious. So, any subset of the population is called an event. This is just terminology. So we say that the event occurs if the random variable lies in S and does not occur if the random variable does not lie in S. For example, suppose you have a population and you take the subset of all females. And in a random draw, if the random draw is female, then the event has occurred. If it is a male, then it has not occurred. So what is the probability of such events? Well, you just add all of the elements in that event and you get the probability. So if you have a random variable which is 1, 2, 3, 4, 5, 6, all being equal, this is like a dice roll. So then if you ask what is the probability of an even number, 2, 4 and 6, so you just add the three probabilities, 2, 4 and 6, that's 1, 6, 1, 6, 1, 6, so that will be 1/2. Now, if you have two different events, two subsets, again the same rule applies. You can add the probabilities, provided that they don't overlap. If the two sets overlap, then you will double count those things which are in the intersection. So in that case, the two sets, you take the union of the two sets, and then you have to subtract the intersection to get the probability. And finally, this rule also has the implication that the probability of a set and the probability of its complement must add to 1. Either the event happens or it does not happen. So the probability of these two must sum to 1. That's all. These are all the consequences of the addition rule. Now, the multiplication rule, if you have independent random variables and you have an event for each one of them, so event is a subset of the outcomes. E1 is the event for x1, which means it's some subset in the set of outcomes of x1. E2 is some subset of the set of outcomes of x2, etc. And so you ask, what is the probability of all of these events happening? What's the probability that x1 takes a value in E1, x2 takes a value in E2, and so on? Then it's just the product of the probabilities. This is the famous multiplication rule. This does require independence. You have to make sure that the random variables are independent, otherwise the multiplication rule does not work. And there are many examples of real-world mistakes people have made in calculating probabilities because they applied the multiplication rule to events which were not independent. So, the addition rule applies to the situation where you're taking any one of the events may happen. This is the union of the sets. If any one of them happens, then the union happens. And so that then you add. Here we are applying the rule to the intersection of the events. That is, all of them must happen. If all of them must happen, then the multiplication rule applies. Also, in the multiplication rule, you need independence. In the addition rule, independence is not needed. So, on the basis of this discussion, now we are going to analyze the properties of IID sequences of coin flips. IID stands for independent and identically distributed. So we have a sequence of coin flips. Each coin, when it is flipped, it comes out heads or tails, and every flip is independent and identically distributed. The ID refers to the fact that the probability of heads must remain the same. That means the distribution is the probability of head or tail, and this distribution must remain the same for identical distribution. You also have INID situation, independent but not identically distributed. That's also it's not that difficult, but it's easier to handle the IID case first. So when you have sequences of coin flips, it's convenient to model this as being a sequence of random variables with the outcome being 0 or 1 and not H or T. And there is a reason for that, a very simple reason for that, because you can add these numbers and you can't add H and T. So in this situation is a very widely applicable situation, this random variable. It's used in many real world applications. So there is a name for this. The 1 is called a success and the 0 is called a failure. It doesn't matter. I mean, it doesn't matter what it is. And you could say that, okay, if someone dies, that's a success. And 0. This is arbitrary labeling. It's not. It doesn't have to do with the English language meaning of success. This technical terminology. So 1 is success. Success is always probability P. Again, this is very commonly used. This letter P is used for success, and Q is used for failure. Q is obviously 1 minus P by the addition law. So if we take the sum of all of these variables, x1, x2, xn, that's called S. That's the total number of successes. If however many zeros you have, they will not add. So however many ones you have, that will add. So you will get the number of successes when you just add all of these random variables. So now what we are going to do, basically all of this lecture is about computing probabilities related to S. And in fact we will not be able to finish. This is the famous binomial random variable, and we will deal with the full complexity of the binomial in the next lecture. In this lecture we just deal with some very simple special cases. So suppose I have x1, x2 up to xn IID random variable. How many outcomes are there? How many possible outcomes are there? Well, every sequence of zeros and ones is an outcome, because you can have either 0 or 1 on every trial. So if you have 0, 0, 1, 1, 0, 1, 0, dot, 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 up to 1, that's one outcome. Since in every position you have two choices, so basically the number of total outcomes is 2 to the n. So just to illustrate, if you have just 3 flips of a coin, then you have 2 times 2 times 2, 8 outcomes, and they are listed over here: 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. Does anybody recognize the sequence? What is the sequence? This is actually the all 8 outcomes of a coin, but it is also something else that you should know from your mathematics courses. You have studied this in 6th, 7th grade, I think. No, this is not permutation.
Sequence?
Yes.
Series?
This is a series. What kind of a series is this?
Arithmetic or harmonic geometry?
नहीं, harmonic geometry. तुक्का मार रहा है बच्चा. What?
Sir, sequence and series पढ़े तो भूल गए.
Yeah. This is just counting. गिनती करना. 1, 2, 3, 4 आती है. कितना आता है? वो तो नहीं भूल गए. वो फर्स्ट ग्रेड में सीखा था. मैं एक बार वो फ्रैक्शंस का क्वेश्चन दिया अपने क्लास को, तो रीवा सॉल्व मैंने कहा क्या सर, मैंने कहा यार हमने 6th ग्रेड में पढ़ा था सर, अब तो भूल गया बिल्कुल. अच्छा, अलिफ बे भी फर्स्ट ग्रेड में पढ़ा था, वो भी भूल गए. तो दिस इज काउंटिंग. 0 0 0 इज जस्ट 0. इसके बाद 1. अब बाइनरी जो नंबर्स होते हैं तो उसमें 1 के बाद 2 आता है, मगर 2 तो है नहीं, तो उसको 10 बना देते हैं. नेक्स्ट 10 के बाद फिर 11 आया. 11 के बाद अब ये 11 99 की तरह से, अब वो 100 हो गया, फिर 101 हो गया. फिर यानी अब 1 जब आ गया तो अब फिर से सेम काउंट है. 0 1 1 0 1 1. समझ गए या नहीं समझे? This is counting in binary. So basically with 3 digits you have 8 possible outcomes. If you go to 4, then you see you take all of the 8 and you append a 0 in the first place, that will be 8, and that will be the first 8 numbers. Uske baad phir 1 dal doge to that will be 9 exactly, and 8 more, so 8 plus 8 is 16. So what is 1000, which is the next number, yani in binary? 1000 in binary, what does it correspond to? 1000 is 8. You see, it starts with 0, so you're offset by 1. At the number 7, you have 8. You have 8 different configurations. Because you are starting with 0. 0 counts as the first configuration. So basically, the total number of outcomes is 2 to the n. अगर यानी कंप्यूटर्स में भी होता है कि 4 bits and 8 bits, 64, 32. So now there's a reason for focusing on this binary, because it allows us to do some combinations which we'll discuss later in the next lecture. Now suppose I look at one outcome like 0 0 1 1 0. अभी 5 n equals 5 ले रहे हैं, तो इसकी क्या probability होगी? It's very simple. You just take the probability of each outcome. 0 is q, the second 0 is q, the third 1 is p, and q. So it's q to the power 3 and p squared. So that's the probability. Now, what's the probability of 0 successes? All 5 zeros. Well, that's q to the 5, or 1 minus p to the 5. What's the probability of 5 successes? That's p to the 5. It's very simple. So, nothing difficult here. Now, what's the probability of 1 success in 5 trials? Well, there are 5 different ways of getting 1 success. You can get the success in the first trial, and in the second, and in the third, and the fourth, and the fifth. Since we are looking at only exactly 1 success, these are the only 5 cases. समझ गए? So each one की probability we know. It's basically p is probability of success, so that's 1 times, and then q has to happen 4 times, so it's p times q to the 4th. And there are 5 cases, so the probability is 5p q to the 4th. And now you can generalize this to n trials easily. So the probability that S has outcome 1 is going to be n, because there are going to be n different cases, and times p times 1 minus p to the n minus 1. This is the formula for 1 success in n trials. Now, suppose event E has probability 5%. That is equal to 1 over 20. This is actually close to the probability of the birth of twins. And I have given in the lecture notes, the example is given in this way. It turns out that it helps for students to be thinking in concrete and practical terms, helps to understand as opposed to abstract That's why it's useful to give examples for a specific situation rather than in general abstract algebraic terms. So suppose that there are 20 births in a hospital. So how many twins will be born? Well, on the average, it should be one. One should be twin, and 19 cases should be non-twins. But what does this mean? I mean, this is a long-run frequency. It means that if you have hundreds and hundreds of births, then this is the number. If you have exactly 20, we can't really say what's going to happen. And so, we can calculate these probabilities. First of all, we can calculate what is the probability of no twins. Probability of no twins, well, that's exactly, if you look at twins as being your success and non-twins as being failure, so twins is 1 and non-twin is 0, then we are asking what is the probability that all 20 cases are 0, right? So all 20 cases are 0 means that 0 probability is 0.95. We have to multiply it by itself 20 times. That's 0.95 to the 20. I did this in Excel, and the answer comes out to be 35.85%. So it's about 36%. So the probability that no twins will be born is about 36%. What about the probability that one twin is born? So that is, according to our formula, again it's n, which is 20, times p, success probability, 0.05, times 1 minus p, which is 0.95, raised to the 19th power. So you can calculate it, and it comes out to be 37.74 or 38%.
Sir? Sir, जहाँ पे हमने वो calculate किए, sir, with no twins. Sir, raised to 0.95 raised to power 20. Sir, we don't multiply it with 20 here.
जो 0 वाला है?
जी sir.
नहीं, क्योंकि वो तो एक ही केस है. All 20 zeros. That's important to understand. Why are we multiplying with 20? Because if you want to get one twin, there are 20 ways to do this. The first birth could be a twin, the second could be a twin. There are 20 different ways in which you can get one twin. There is only one way in which there are no twins. All of them are 0. There is no other way. So there is only one sequence which produces S equals 0. There are 20 sequences which produce S equals 1, and basically the issue in binomial probability, which we won't discuss in this lecture, we will in the next, count how many sequences are there in which S equals 2, and that's a little bit of a complicated problem, so that we will not solve in this lecture. So one thing interesting to note here is that frequently people think that since the event has probability 5%, then the probability of one success will be very high, because that's 1 out of 20. So ठीक है, exactly नहीं आता हमेशा, मगर most of the time you should get it. But this is not true. You're getting only a 38% probability. In fact, what the law of large numbers says is that the ratio will be close to the true probability. But being close doesn't mean being exactly correct. And the probability of being exactly correct becomes smaller and smaller, actually, even in large samples. You just come close. Instead of, you see, here we are talking about 1 out of 20. In a larger sample, you could talk about 5 out of 100 or 50 out of 1,000. So what's the probability of getting 50 out of 1,000? Well, it's going to be very low. It's not going to be. It's not going to increase. Getting the exact right percentage is unlikely and becomes less and less likely. Probability actually goes to 0. Coming close to the exact percentage is a high probability event, and so if you talk about, instead of saying 50 out of 1,000, you say between 40 and 60 out of 1,000, then in that range you will hit a lot of, there will be a lot of probability. There is still something which is true about this intuition, which is that if you look at all of the different cases, the one which is exactly correct always has the largest probability. So this is 38%, it's bigger than 0, and it is also bigger than 2. But the probability itself will keep going down, even though it's the largest one of all the possible ones. So basically this is something which is often confusing and will remain confusing. I mean, students don't get clear on this point for a long time, but even though the event is likely to occur 1 in 20 times, and we can think that on the average every 20 trials you will have one twin, but exactly there is a lot of random fluctuation. In any particular 20 trials, anything can happen. You can have 0 twins, you can have 1 twin, you can have 2, you can have 3, 4, more. What's the probability of having 2 or more twins? Yes, I'm asking a question.
That is multiply.
नहीं, multiply करने से
20 into 0.05 square.
2 or more I am asking. 2, 3, 4, 5, 6.
2 or more?
Yes. Yes, you have the case of 0, which is 36 and 38, so everything else is 2 or more. So you add 36 and 38, that will be 73%, and 1 minus that will be like 27%. So 27% probability of 2 or more twins. Another example like this one. So suppose Imran Khan hits 6s with probability 20%, 1/5. What is the chance of exactly 1 6er in 3 overs? So again we just apply the formula. In 3 overs you have 18 balls. Now you want the probability of, so basically it's 18 is n, so you take 18, you multiply it by the probability p of success, which is 1/5, and then 1 minus p is 4/5, you raise it to the 17th power and you get 8.1%. Now I haven't told you how to calculate it, but what if we calculate what is the probability of having 2 6s, then will that be higher than 8.1% or lower than 8.1%? This is it will be higher. You see, first you have to think, what is the normal number of 6s he will hit in this 18 trials? What is it? 1/5 probability hai. So hits 20% of the time. So what is the number? What is the expected value? What is the average value?
20%.
No, there are 18 balls.
18 balls. Yes, sir.
So
18
18 divided by 5, which is 3.6. So it is expected that he will be hitting about 3.6. So probability of 1 6 is low, 2 will be higher, 3 will be even higher, and between 3 and 4 you will get the maximum. 3.6 means that most likely 4 will be the maximizing value. After that the probabilities will start going down. 5 pe kam hogi or 6 pe aur bhi kam hogi, and so on. Got it? Understood? Alright, so in summary, if we have random draws, actually these are random variables, and if I take the sum of all of them, this is actually called a binomial random variable with n trials and success probability p. We will discuss this in much greater detail in next lecture. In this one we have just made a start on this binomial, and so we have done two cases. One is that what is the probability that S is 0? That is just one case, so that's 1 minus p to the n. Also the case where all of the trials are successes, that's easy to compute. So the probability that S equals n, that's just p to the n, because again there's only one case in which you can get n. Now if you want to look at one success, that is np 1 minus p to the n minus 1, just as we have shown. And also on the other side, if you want to look at the case where there is exactly one failure, that's S being n minus 1, and that's just like the same formula, except that the p and 1 minus p become switched. So you have n minus 1 successes and 1 failure, so p to the n minus 1 times 1 minus p and times n again, because there are n possibilities. So these are the 4 formulas that we have derived. The case where S is 2 or 3, etc., this we will handle in the next lecture. In addition to the formula, I am trying to give you some intuition as to the value of these numbers. What are how big these are, how often this happens. So this is something which it requires more work to understand. But one of these things is that the exactly correct ratio, the probability of this keeps declining. This is again bit paradoxical, because students think that the exact correct ratio, because the law of large numbers says that the observed frequency will converge to the exact right ratio, but this doesn't mean that the exact right ratio itself has a high probability. It means that near the exact right ratio you have lots of probability, but the exact right ratio itself has probability going to 0. Actually, it keeps becoming smaller. Okay, one case that I want to discuss is called the Poisson distribution. This is called the law of rare events. This is a case we have been discussing some time earlier also. This is the case where p is small but n is large, so the probability of success is very small, but there are a large number of trials. So because of this, it will happen. So this was first documented by somebody who looked at deaths due to horse kick in the Prussian army. So it's a very unlikely event, but it can happen. And if you have a large army and thousands of soldiers, then even if the probability is 1 in 1,000, if you have 3,000 soldiers, then 3 of them will die due to horse kicks, so on the average. So the number of road crashes, now the probability of accidents is quite low, but if you have millions of cars, then there will be crashes. Similarly, the probability of cancer is like 1 in 100,000, but if you have a population of million, then you will have 10 cases. If you have a web server, it has hundreds of documents in it. The possibility of you get people are accessing the website and then they are asking for downloading some document. Any one document has very low chance of being hit, but there are hundreds of thousands of hits. So again, this is a Poisson distribution. Somebody analyzed the outbreak of war. Now, war is a rare and unusual event, but with lots of countries and lots of possibilities. It can look like a Poisson. If you look at the request for telephone calls at a switchboard, then there are hundreds of people. There's thousands of people in Islamabad. Only everyone has a small probability of calling the switchboard, but there are so many of them that something is likely to happen. So this is the Poisson situation. Now we are going to calculate these probabilities. They are related to the binomial, but a little bit different, and that's what. But you can derive them from the binomial. That's what we are going to do. So before we do that, we go back to a little bit of math. The exponential function is defined as, if you take any x, 1 plus x squared over 2 plus x cubed over 3 factorial plus x to the 4th over 4 factorial and so on. This is the definition of the exponential function. Now this is a little bit mysterious, and actually because nobody can sum an infinite series, so it doesn't seem like this is a reasonable way to define a function. So actually you have to think of this as a rule to compute the function. In fact, this is how to understand functions. A function is defined by, take an x, you do this to it, and you will get the y. So this has to be a rule, and also it has to be a rule which can be used. So far, if I just write the series, this is not valid. Not valid in the sense that it doesn't tell you how to compute the function. And when I want to say that here is a function, then I have to tell you how you can calculate this function. If I can tell you how to calculate, then I have done the job, I have defined a function. If I don't, then I have not defined a function. So, as it happens, in this function, you can prove that as the series becomes larger and larger, the terms become smaller and smaller. So if you just take a finite number of terms, you will get a good approximation. Now, this is just a general principle. How many terms do you need to take, and how good the approximation will be? Both of these are things that need to be considered. Now suppose I want to compute this function accurately to 2 decimal places. Then, if the value of x is small, I only need to look at the first term, 1 plus x. Why? It's very simple. If you look at x equals 0.01, then x squared is 0.001. This is only coming into the 3rd decimal place. So up to, if I'm interested in 2 decimal place accuracy, x squared will not matter. X cubed will be 0.0001. So again, this is in the 4th decimal place. Makes no difference. So all of the terms after x are not going to affect the 2nd decimal place. So basically then I have a rule which works for 2 decimal place accuracy, just 1 plus x for small values of x. If you have larger values of x, you need more and more terms. Here is a table of the first term and the 2nd term, 2 term and 3 term approximation. The x is actually, now one rule which is sort of cheating is we can call Excel and we can say x, and that will tell us what the exponential function is, and that is what I have done in the first column here. But actually, of course, how did Excel compute this? It used these rules that we are discussing. So the value at 0 is 1, and that's something that's perfectly clear, because if you look at those terms, for x equals 0, all of the terms are 0, so this is exactly correct value. Now when you go to 0.1, you can see that the exact value of the exponential function is 1.10517. This is to 5 decimal places. but the one-term approximation is accurate up to 2 decimal places. And similarly, if you go back minus 0.1, minus 0.2, the first term approximation is good near 0 and becomes gradually worse as you move further away. If you look at the 2-term approximation, at 0.2, it's 1.22000, which is only a little bit different from 1.22140. It's accurate to 2 decimal places. And at 0.3, it's also accurate. But at 0.4, it's off by 0.01. So it's now not as accurate. But if you go to the 3-term approximation, it's still working fine at 0.4. So as you move further away from 0, you need more and more terms. This function is so important that it has been tabulated a long time ago, hundreds of years ago. And people have found out a lot of tricks on how to calculate it accurately and how to do it efficiently and so on. Here is the graph of the function. It's very useful to look at, to understand a function you have to know the rule, and then from the rule you can make a table, from the table you can make a graph, and it's very useful to look at the graph to understand what the function is. Now the logarithm function is the inverse of the exponential function. This inverse means that if you apply exponential and then you apply log, you cancel the operation. So the logarithm of the exponential of x is x. That is the definition of the inverse. It undoes the operation. So inverse, people often sometimes make mistake. I mean, they think that, for example, 1 plus x, the inverse is 1 minus x. That's not true. You have to undo whatever is being done. So square root ka inverse square hai, magar there are some complications. Anyway, so x of 1 plus x, x of x is exponential of x is 1 plus x for small values of x. So this has implication for the log function. Log of x of x equals x. So if x is small, then x of x can be replaced by 1 plus x. So it means that log of 1 plus x is equal to x for small x. So x of x is 1 plus x, and log of 1 plus x is x. It's just the natural thing for the inverse. Similarly, we know the product rule for exponents. X of x1 plus x2 is equal to x of x1 times x of x2, and this translates to the very well-known rule for logarithms, that the logarithm of a product is the sum of the logs. This was the basis for the slide rules, where you can take to calculate a product, you first calculate the logs, then you add the logs, and then you take the antilog. This used to be the methodology for calculating products in the days when there were no calculators and no computers. Probably you are too young to know this or to have seen this, but engineers used to have these slide rules which they used to calculate because there were no calculators. And so the slide rules were based on this property of the logarithm function. But then they became obsolete, and then the calculators came. Now, we are going to apply these rules to calculate the Poisson probabilities. So in the Poisson probabilities, you have n large and p small, and so we want to calculate what is the probability that s, the number of successes, is 0. No, this is a rare event. What is the probability it doesn't happen at all? Now, as the population size increases, this probability is going to go to 0. But how fast? That's what we want to know. So by the binomial calculation we have already done, this is 1 minus p to the n. Now I'm going to make approximation to this. So first we will take the logs. So we have log of probability S0, that's log of 1 minus p to the n, and that's equal to n times log of 1 minus p. This follows from the product rule. You have 1 minus p multiplied by itself n times, so you can write this as a sum, log of 1 minus p plus log of 1 minus p plus log of 1 minus p, so on, repeated n times, and so it becomes n times log of 1 minus p. Now the crucial thing is that we approximate log of 1 minus p by minus p, because p is small. This is the guarantee for the Poisson, that p is going to be very small. So in that case you get minus pn. Now pn is a very important quantity in this Poisson case, because pn is the expected number of events. P is the probability which is low, n is the number which is large. We multiply them together, and that's the number that of events that you expect to see. This is called lambda. Lambda is the expected number of events, the average number of events that happens. So if p is 1 over 1,000, n is 1,000, lambda will be 1. You in 1,000 cases, you will see only 1. If n is 2,000, lambda will be 2, and so on. So the probability of zero events is just take the exponent on both sides, so it's e to the minus lambda. Now in the same way we can do the approximation for S for one event. So if I want to calculate the probability of one event, that will be, first we take the log, so it's log np 1 minus p to the n minus 1. Now remember that np is lambda, so I take log of lambda plus log of 1 minus p to the n minus 1. Now I can take the n minus 1 power down, and it becomes n minus 1 log 1 minus p. Again, I replace log 1 minus p by its approximation minus p, and so I get log lambda minus p times n minus 1, which is log lambda minus lambda plus p. But p is very small, so I can ignore it. So probability that there is exactly one success is lambda e to the minus lambda. And similarly, you can make more complicated calculations, which I will not do today. It will be part of the next lecture, perhaps. That if you want to look at what's the probability of k successes. So k will be very small. I mean, this is the important thing about the Poisson. N is large, k is small, because you will not see too many rare events. You will see 1, 2, 3 maybe. So anyway, the probability is lambda to the k e to the minus lambda over k factorial. This is the Poisson distribution. Now yes.
Sir, lambda के साथ negative sign क्यों है?
Oh, this is just the way it comes out when the calculations. Yani.
So, but theoretically, can we understand it? Otherwise, just depends on.
Well, you see, e to the minus lambda is a positive number. So you start by log 1 minus p, and that's approximately equal to minus p. See, e to the 0 is 1. So any number less than 1 has to be e to the minus something. And these are probabilities, so it will always be e to the minus something. If you have e to the plus something, that is guaranteed to be bigger than 1. and it can't be a probability. Okay, so this is a standard type of Poisson problem that is set. A small life insurance company has determined that on the average it receives 6 death claims per day. Now remember that insurance company insures hundreds of thousands of people. Probability of death on any given day for any one person is very small, but if you have 100,000 people, then some of them will be dying. And so it says that this is 6. So 6 is your lambda now. It means that this is the average number of claims. So then, if you want to calculate the probability x equals k, it will be 7 to the k e to the minus 7 over k factorial. So the problem is find the probability that company receives at least 7 death claims. Well, for this you have to calculate probability x equals 0, x equals 1, 2, 3, 4, 5, 6. Add them all up, subtract from 1, and you will get 40%, which is the number. Okay. So that's it. That's all for today. And okay, subhanallah bihamdihi, subhanallah.